I want to take a few minutes to talk about how we describe motion using vectors, and in particular to talk about how we use unit vector notation, this I hat, j hat, k hat business that a lot of textbooks use to talk about motion and to talk about vectors. So to begin with, let me just present to you a typical looking equation for the motion of some particle. R vector as a function of time might be written as, and I use units all the time. I love units in my equations. Some textbooks will leave them out. I hate it. So I'm going to write 2 meters per second squared times t squared times I hat plus the quantity 1 meter per second cubed times t cubed minus 4 meters per second times t all times j hat minus 2 meters times k hat. That is an example of a function describing the position of a particle or some object as a function of time. What do I mean by that, by describing a position? Well, let's double check. Every one of these terms, if I plugged in a time in seconds, would come out to be, this would be like if the time was 1 second, say, this would be 1 second squared times 2 meters per second squared. The seconds cancel out and I get 2 meters. Here, I would plug in time equals 1 second and get 1 second cubed. The seconds cubed would cancel out with the units there. I'd get 1 meter, and so on. That's the idea that it's a position. The units always are supposed to work out so that I get units of meters, or whatever units I'm in. I could be doing feet or furlongs if I wanted to, but meters are what we normally use in science. So this is the idea of a function of position, and what I want to do is talk about what this means, what this means physically, and what this notation is getting at. Now, what this I hat, j hat, k hat business really is, what those are really telling us are, you can think of them as little labels telling you about directional information that you can add into your algebra as a sort of seasoning to your algebra. And the fully seasoned algebra then has not just numerical values, but directions along with it. Each one of these, I hat, j hat, and k hat, you can think of as an algebraic constant when you're doing math to this. But visually, I hat, j hat, and k hat all have meaning on a graph. Here I've graphed x and y as my standard first 2 coordinate axes, and if on those graphs, the I hat vector, that little I hat vector, is just a stubby little thing pointing in the x direction. Now I've drawn it to have the length about 1 meter in here, but really I hat is dimensionless. It has no concept of distance. It's just 1 unit in the x direction. That's what I hat means. J hat, similarly, means 1 unit in the y direction, in the plus y direction. And again, I've drawn it to be about 1 meter in this scale, but that's just sort of for convenience. It is 1 unit, and I will multiply it by something with units to figure out how far it actually is. If I were going to draw k hat is in the z direction. I haven't drawn the z direction of these coordinate axes over here just because it's hard to draw 3 dimensions on a board in a way that doesn't just look cluttered. But if the plus z direction were out of the board toward you, if that's the plus z direction, then the k hat unit vector would be a little unit vector pointing out of the board 1 unit in that way. Not 1 meter, but 1 unit. And if I multiplied it by 1 meter, it would be a meter long pointing out of the board. That's what I hat, j hat, and k hat are trying to be. We'll talk about how to interpret them in a minute, but that's the concept. Let's look at this function now. To understand a function, I like to plug in some values just to get the gist of what it does. So let me try that for some values, some integer values of time, plugging them in here. If I plug in time equals 0, this first term is 0. So this gives me a 0 I hat. I could just write that as 0, I suppose, but just for it to be clear, I'm going to write the 0 I hat. If I plug in time equals 0 here, I've got 0 minus 0 in the parentheses, so that's plus 0 j hat. That's supposed to be a j, really. And then no time here, so minus 2 meters k hat would be what I get there. So this is a point at, if I want to write this in coordinate notation, or in ordered triplet notation, I could write this. Some people write the vectors with angle brackets. They might write 0, 0, minus 2 meters as that vector. This means the same thing. It's just 0, 0, minus 2 meters, x, y, z, I hat, j hat, k hat. This form implicitly has the directionality in it and sort of in the notation. This form, the directionality is built into these little unit vectors. that are written there. You can think of it either way. I'm going to use this notation, but either form is fine. So I'll keep going. What if I plug in time equals 1 second? 1 second, I just did this a minute ago, right? This is 2 meters I hat. Plugging in 1 here, that's 1 meter minus 4 meters is minus 3 meters j hat. And this is a constant, minus 2 meters k hat. So this is 2 minus 3 minus 2 in meters in coordinates. And I'll visualize this in a minute. At 2 seconds, 2 times 2 squared is 8. So that's 8 meters I hat. 2 cubed is 8 here. Minus 4 times 2 is 8 here. And the units come out again. That gives me 0. Again, I could just leave it out, but I'll say 0 j hat minus 2 meters k hat here. So I've got that for my 2 second point. And then 3 seconds, just continuing on this one more. 3 squared is 9, 18 meters. 18 meters I hat. 3 cubed is 27, minus 4 times 3 is 12, that's 15. So that's plus 15 meters j hat minus 2 meters k hat. Okay, so I've got a list of points now. I've got a list of points that I have for these various times. And if I want to graph this, if I want to graph this motion, all I have to do is just plot some points. That's a good starting point for graphing motion. And so let me do that. I've just got x and y here, as I said earlier, and my z behavior is really boring anyway. It's just a constant negative 2 meters. So 2 meters behind the board, but otherwise, it's constant negative 2 meters. I'll just ignore it. So I'm just going to graph x and y. In your heart of hearts, you should know there's a z as well. So, okay, at time equals 0 seconds, I'm at 0 x and 0 y. So this is time equals 0 seconds right here. At time equals 1 second, I'm at 2 meters I hat minus 3 meters j hat. 2 minus 3. At time 2 seconds, 8 meters I hat, 0 j hat. Still my constant. 6, 7, 8. That's over here. At time 3 seconds, 18 meters I hat, 15 meters j hat. So 18 I hat, try to get this about right. 15 j hat is about there. Those are my points. Those are the points that I've plotted. And if I were to fill this out, if I were to do a half and 1.5 and 2.5 and 0.1, 0.2, I'll fill it in more and more, I would find a nice pattern that looks kind of like this. Oh, that didn't bend quite the way I wanted it to. It's a little interesting, actually, the way this works. I think that maybe I arced down too much here. You can already, even just trying to smoothly connect these things, you can get a sense of how nature is trying to get these to connect and what that curve must look like. Something like this, anyway. So I've got a curve that's going to look something like that. And just for the record, if I were to plug in negative numbers for time, t squared wouldn't change, t cubed and t would change, and my constant wouldn't change. They change sign. So if I were to plug in, let me just put in a plus or minus here. If I said this was plus or minus 1 second, the I hat and k hat parts will stay the same, but this will become negative. So minus or plus, that means if it's plus 1 second, it's minus 3 meters. If it's minus 1 second, it's plus 3 meters. The top sign matches the top, the bottom matches the bottom. If this were plus or minus 2 meters, that's the same, it's just 0. If this were plus or minus 3 meters, it would be plus or minus 15. So I can just run this backward. Just for convenience to see the whole path, that means I'd have at negative 1, I'd have, so this was going this way, increasing time, looked like that. At time equals negative 1 seconds, I'd be at 2 and plus 3. It's just going to be reflected. That's going to be 8 and 0 for negative 2 seconds, and 18 and negative 15 over here. So you know what this is going to be now. Okay. Oh, whoops, not well. I guess if I want to have increasing time, if I want to always label increasing time, it's going to go like this. That's my path. That's what I could graph from time equals -3. This is time equals -3 seconds up through time equals +3 seconds. That's my graph from -3 to +3 seconds. It's going to loop-de-loop around. That's the difference when than with ordinary functions just of y of x. If you're parameterizing both in terms of time, you can have loop-de-loops and things. That's allowed, and it's good, because in nature, things can do loop-de-loops. So okay, we've got all this information about the position as a function of time. And after you've done that, the natural question is, how is it, that's the position. I ask, what's its velocity? How is this moving with time? And let's see. Well, by definition, velocity as a function of time is the derivative of the position with respect to time. That's how velocity is defined in vector language. And the beauty of this unit vector form is that we can directly just apply derivatives to it in the way that we learn in calculus class. I've got this rule over here for derivatives, just to remind you, for polynomials of time. Constant, if I have a function that's a constant times t to the n power, then the derivative is n times the constant times t to the n minus 1 power. That's just a familiar thing. So if I have a great big x hat, I hat, j hat, k hat function for position, all I have to do is take the derivative of each term one by one. That's how derivatives work. You just spread them out along these terms. And so doing this, remember, I hat, j hat, and k hat are constants. They don't change with time. Those are just the x direction, the y direction. Thank goodness we aren't using polar or cylindrical coordinates or something, because then there are some weird things that show up. But we're not. We've got, I guess they don't change with time anyway. So yeah, we've got these simple things. We've got coordinates that stay here. So what is this? The derivative of this term, it's a t squared term, and my constant is 2 meters per second squared times I hat. I hat is part of the constant. So the derivative will be 2 times 2, I would write this normally, 2 times 2 meters per second squared I hat times t to the 1. And then here I will have plus, and I can simplify that, right? Maybe I'll even, just for the sake of a simple, writing things down in a simple way, I'll simplify that. I'll just say that is 4 meters per second squared times t times I hat, because that's t to the 1. And here, inside the parentheses, I have 3 meters per second cubed. That's my n is 3 here. 3 times 1 is 3 times t squared minus, that's t to the first power, so that's just the constant 4 meters per second j hat plus 0 k hat, because 2 meters and k hat are both constants, and you can think of this as being times t to the 0 power, and so n is 0 and the derivative is 0. So okay, I've got that, that's 0. So this is my velocity, and I can, again, plug in some points, plug in some numbers to see what I get. I know my k hat is 0 all the time. I'm just going to ignore it because that z coordinate isn't changing at all. I'm just going to write I hats and j hats down here. So time equals 0. I get 0 I hat. And time equals 0 minus 4 meters per second j hat. 0 minus 4 meters per second j hat. Cool. For time equals 1 second, I get 4 meters per second I hat. And then 1 is 3 minus 4 minus 1 meter per second j hat. 0 k hat. For time equals 2 seconds, 2 times 4 is 8. 8 meters per second I hat. And 2 squared is 4. 12 minus 4 is plus 8 meters per second j hat. And finally at 3 seconds, that's 12 meters per second I hat. 3 times 3 times 3 is 27, minus 4 is 23, plus 23 meters per second j hat. There I have my full list of velocities at these different times. And I guess if I'm doing my plus or minus, this term is going to go negative if I do a negative time. These terms will stay the same because negative squared is a positive. So my x is going to be the plus or minus here. So I guess this will be plus or minus on my x's every time. That's always 0, plus or minus 0. Let's see. So, okay, let me see if I can visualize that. At time equals 0 seconds, I've got 0 minus 4. That's all in the negative j hat direction, all in the negative y direction. That means my velocity at this moment is all in the negative direction. And sure enough, that matches, that's tangent to my curve at that point. Similarly, at time equals plus 1 second, so I'm dipping down there, my x component is plus 4, my y component is minus 1. So this is mostly to the right, a little bit down. V of 1 second. And that matches my graph as well. It's moving to the right and a little bit down at that point. Or at 2 seconds. That's a 45-degree angle, plus 8 in the x and y. So at this point, I'm expecting a very big, fast V of 2 seconds going up that way. You see how this is even faster once I get to 3 seconds. You get the idea of this, though. That looks like a 45-degree angle, even in my sketch. So the velocity vector is always going to be tangent to the path, your loopy path, whatever it is. And in this case, we've got an equation for it. It comes out, if I draw these vectors on the picture, I get a good visualization of what's going on. So I could do that for the negative times as well, but it's probably not worth it to clear out my picture that way. And then finally, I guess this is the part where I then find what's the acceleration. Acceleration is just the derivative of velocity, how the rate of change of velocity with respect to time. And again, I just take derivatives. I do my same process. That's t to the 1. So this is 4 meters per second squared. I hat, remember that's a constant. I hat's part of my constant. And over here, that's going to be a constant, so its derivative is 0. This part will give me plus 6 meters per second cubed times t times j hat, still 0 k hat. That's my acceleration as a function of time. I've got that worked out. And so, again, that's my acceleration vector just by taking those derivatives of the velocity vector. And when I do this, I can plug in my points at time equals 0. This is 4 meters per second squared. My units are still working out. That's great. And time equals 0 plus 0 j hat. Cool. Time equals 1. 4 meters per second squared I hat. Time equals 1 plus 6 meters per second squared j hat. Time equals 2 seconds. It's going to be 4 and 12. 4 meters per second squared I hat plus 12 meters per second squared j hat. And 3, I'll just go ahead and do it. 4 meters per second squared I hat plus 18 meters per second squared j hat. You get the idea. And of course, if I do my plus or minus, if I did negative times, this is going to constant, it's not going to change. This would go negative, so my j hat terms will possibly be negative, plus or minuses on my j hat terms. And there, I guess, what's my acceleration look like? Let me draw that in. My acceleration at time 0 seconds is 4 I hat, 0 j hat, so it's 4 meters per second I hat, so it's all in the x direction. And again, if I draw that over here, I've got too many colors that look the same. I'm going to do my acceleration arrows in red because it'll fight with this I hat. I'll get rid of the I hat. We don't need that right now. I want to focus on motion at this point. So at time equals 0, 4, 0. That means I have an acceleration going like this. Acceleration at time equals 0 is that way. This agrees with things we've seen in class before. This agrees with things we know, that if we're moving in changing direction, the acceleration vector should always point toward the center of the curve that we're curving around, toward the center of a circle in circular motion, toward the center of the curve. So that actually agrees with what we've seen in class with motion diagrams or other ways of analyzing motion. That's great. What about time equals 1 second? 4, 6 meters per second squared. So a little more plus y than plus x and pretty big. 4, 6. Something like this. This is a At 1 second, again, it's pointing right in toward the center of my curve. At time 2 seconds, 412, okay, that's 3 times as much vertical as horizontal. So if I do, okay, I've got a big, well, that's too vertical. Whoops. Got to have some angle to it. This is my acceleration at, whoops, didn't write, well, acceleration at 2 seconds. Again, let's think about this one. By this point, my acceleration vector is not pointing very perpendicular to my motion at all. It's pointing actually pretty close to parallel to my motion. It's going to arc me a little bit, but more than anything, that acceleration vector is going to reinforce my velocity vector. When acceleration and velocity vectors point nearly the same direction, that means you're speeding up. And so I'm going to go faster and faster, and that agrees with the picture of the motion that I've seen. So all the things we've seen here, all these descriptions, do a great job. All these vectors plugging in numbers match beautifully the intuition that I have for how motion works in 2 dimensions or 3 dimensions if you wanted to go to 3 dimensions. It works out very nicely, position, velocity, acceleration, taking derivatives mathematically, and then if you draw them, you'll see that it agrees with our intuition for motion we've developed in other ways. Along similar lines, maybe the one other thing I want to comment on is talking about vector magnitudes, just because some people have asked me about that. How do I find the magnitude of, let's say I want to find the magnitude of this velocity vector right here. 4 meters per second I hat minus 1 meter per second j hat, that's a velocity vector. So what if I want to find the magnitude of the velocity measured at time equals 1 second? How do I find that magnitude? Well, let me look at my vector. It's 4I hat minus 1 j hat. I've drawn it here. Let me copy it down over here. And I'll just draw in. I know it is 4 meters per second in the I hat direction. That's basically 4 units of I hat. And then I added to that minus 1 meter per second. 1 meter per second's worth of negative j hat. And because this is I hat and j hat, x and y, they're perpendicular. And I have a right triangle all of a sudden. So what's the advantage of a right triangle? Well, suddenly I've got all sorts of power that I can use to describe this. What is this magnitude? This is the magnitude. It's the length of the hypotenuse of this right triangle. And it turns out I can just do the Pythagorean theorem. The square root of 4 meters per second squared plus 1 meter per second squared. That square root, that's the Pythagorean theorem. And what is that? Square root of 17? Square root of 17 meters per second is my magnitude. I guess I need to work that out. It's going to be like 4.1 or something, 4.05. I don't know. Something small. It's going to be 4 point something small. So this is going to be about 4.06 meters per second. I don't know. Meters per second. I guess I could work that out right now. You can work it out yourself. It's going to be something small. Anyway, something in that neighborhood. That's how you find that. If I want to know the angle, what is the direction? I could say, well, here's an angle compared to the plus x direction. I can just draw it in my picture. And I can say that my angle is, well, I know that tangent of theta is equal to opposite over adjacent, which for us will be negative 1 over 4. So theta is the inverse tangent, or arctangent, of opposite over adjacent, negative 1 meter per second divided by 4 meters per second, or the inverse tangent of negative 1/4. And again, you can work out what that angle is. Brilliantly, I have not worked it out in advance. I don't have a good guess. It's got to be some negative angle. I don't know, negative 18 degrees? I'm really not sure. I'm guesstimating from my picture, really. My picture is probably not even all that good, but something like that. You'll get some angles. You'll get a magnitude and a direction if you want to do that for any vector where you have a specific I hat j hat form. Similarly, if you knew the hypotenuse, the magnitude, and the angle, you could find those sides, those components, the x hat and the y, or the I hat and the j hat components, the x and the y components. You could find them just by doing some trigonometry with sines and cosines. that's how we do problems in here. That's how we analyze motion with vectors. That's what these unit vectors are all about. Think about right triangles and Pythagorean theorem and trig anytime you want to go back and forth between magnitude and direction and components. Think about just derivatives, connecting these different ideas, relating to our graphical intuition if you want to look at an actual full motion and analyze it using these sorts of tools.